All right, good morning, everybody, or afternoon, sorry. I apologize for the lateness of getting this posted, but I did promise that I would have a video for you guys for ionic bonding, sort of writing names, writing the formula so you can get used to it. We're also going to cover a little bit about covalent bonding as well as some naming acids and writing their formulas. But let's go ahead and jump into it. Now, part of what we remember we covered the other day is we talked about using the crisscross method. Now, basically the idea was we write the cation, the metal, first, the anion afterwards. After we've done so, we write their ion symbols. So, in the case of what I have here, I have barium, Ba2 plus, and oxygen, O2 minus. Now, second step, if the charges are the same, we just write the elements as they are, as you see here below. Just write BaO, the charges cancel out because we have a net charge of 0. That's our goal. Now, what do we do if the charges don't actually match up? We have to go a step further. That step further is going to be, we're going to go ahead and take the symbol here, Ba2 plus, but now we have chlorine, which is a Cl minus 1, or 1 minus. What we're going to do is we're actually going to cross and bring them down. So, taking this here, the 2, sorry, that looks a little funny, the 1, and we're actually just going to allow them to switch places. This allows us to be able to see how we actually balance out the charges. And if you can tell, we actually are taken care of. We have 2 chlorine for every 1 barium. Now, this is going to work very similar when we get into naming them. The naming, we're going to keep the name of the cation first, which are going to keep their whole name, and the anion, the nonmetal, or the second element, is going to come next, but we're going to change the ending to IDE, just like we did on Friday. So, the example we had first, we have BaO, or barium oxide. Kept the metal name the same, and changed the ending on oxygen to oxide. Now, what about our second example? Still dealing with barium, so the name, barium, stays the same, but now we have chlorine. We have 2 chlorine. We're going to say barium chloride. Now, there was a good question that was asked on Friday, and it said, okay, so how do I know how many chlorine are supposed to be there? Or in the name, how can I distinguish between it? When we're dealing with ionic compounds, the thing to remember is there's only one way that we can actually put these things together, these 2 elements together, sorry, and they'll have this formula and this net charge of 0. So, with that being the case, I don't have to add any prefixes or any numbers to sort of remind me. I just need to make sure I have my correct subscripts because my charges need to be balanced out. Now, elements with that form only one type of cation, usually going to be the metals, do not need a Roman numeral in the name. What do you mean by that? Well, this is what we deal with for type 1 metals, or type 1 elements participating in ionic bonding. Now, let's go on to type 2. These type 2 metals are going to be the ones that they're actually going to vary a little bit. When you look at iron, there are different forms of iron that we may run into, depending on if it's an acidic, basic, or neutral environment. These things will change. So, in the name of the compound, we change it by making sure there's a Roman numeral to specify that I'm dealing with this specific type of iron or manganese or so forth. So, given the example we have here, oh, sorry, almost forgot. You notice that the number here, the number of electrons it's going to lose, is telling you the charge. So when you think Roman numeral, think this is the charge that it's going to have. And I can move forward with that. Now, let's take a look at this here. If I have an example of iron 3 chloride, so iron 3 tells me that the charge on my iron is going to be plus 3. And the fact that I have chloride, which I know is a -1 charge, I'm going to do just like I would do at any other point. I'm going to go ahead and say, okay, Fe 3 plus and Cl minus 1. I need to cross and bring them down. So my 3 here, bring it down, and my 1, which I don't have to write, but still would bring down to give me my final of FeCl3. Now, I don't have to worry about the Roman numeral in the formula, but I do have to worry about it in the name. So you want to make sure you're paying attention to that as you practice writing these formulas. Now, also the thing that we have to worry about and pay attention to is if we are dealing with these type 2 compounds, this is usually where we run into it, we need to make sure that we write the formulas in the lowest whole number ratio possible. This is where we sort of go back to and look at the formula, look at the charges, and see how we can work them together. So, taking a look at what we have here, we have tin 4 oxide. Now, most people looking at the charges here and here, would say, okay, SN2O4. Now, while that is correct according to the crisscross method, we realize that we can reduce it a little bit more. So if we look at it and see that, oh, we can divide both of them by 2, we know that we're going to get a simpler ratio, and this is going to be more in line with what we have. So the actual formula is going to be SnO2. The way that you'll know this is, if I think back to my Lewis structures, I have Sn, and it has 4 electrons it's going to get rid of. Here we go. And I have oxygen that currently has 6 valence electrons. So that means each oxygen is going to get 2 electrons. Draw another one over here. 1, 2, 3, 4, 5, 6. So when tin donates, I only end up with 2 oxygen for my 1 tin atom. Want to be very, very careful with this, and I know some will look at this for a little bit and say, I'm not fully sure, but continue to look over the different practice problems that we're going to do throughout the week, and I think you'll be a little bit more set in terms of what we're going to be doing here. Now, what about when we're dealing with polyatomics? The biggest thing that we're going to look at with polyatomics is, and this is just a little key, you need to memorize them. Formulas, names, charges, because throughout the test, these are things that will come up, and it is expected that you know them and can then apply them the way that they're necessary, the way that is necessary. So what we're going to use, one of the ways that we use, is a game called Mahjong Kim. For those who like playing Mahjong, sort of get a chance to learn while you play. But basically, it's going to be a matching game that you're going to use to learn the different polyatomics that we're going to work with. Now, the ones on the game, there's still more than that, but I think that'll get you a good base to start with. Now, if we have polyatomics, first off, we have to figure out what is a polyatomic. The polyatomic is going to be basically a covalently bonded group of atoms. Now, why does it have a charge on it? Because it's a polyatomic ion. It's going to be because in some way, shape, or form on one of these ions or one of these atoms, there is not the octet rule is not satisfied. That being the case, it's going to behave a little bit differently. Now, when we deal with polyatomics, the one thing you want to remember is you're going to keep all of it the same. So if I give you the formula NO3 like we have the picture here, you want to make sure that you keep the NO3 together. Other than that, we're going to treat it just like a regular monatomic anion. So, what do I mean? If we look down here, we're still going to use the crisscross method, and we have sodium 1 plus and a nitrate ion with a 1 minus charge. Because the charges are the same, they cancel out to 0, I just write the formula as it is, NaNO3, and I'm done. But if the charges don't match up, I have another step that I have to do. That one step is given to us here in our example, Mg2 plus again our nitrate ion with a -1 charge. I'm going to still do my crisscross method, so I'm still going to bring these down. As you see here, I'm still going to bring it down. But to show that I have more than one of my whole nitrate ion, I'm just going to go ahead and put it in parentheses. This allows me to differentiate and say that it is a nitrate ion, not necessarily nitrogen and oxygen separate, but it's all one cohesive unit. And it's going to be accepting, I have 2 of them receiving electrons from our magnesium ion. Now, we're going to do, again, some practice with this, so do not worry, do not fear. Now, how are we going to take this a little bit further? Now, we have our covalent compounds. These are going to be binary covalent compounds. Binary, again, meaning there are only two elements that are a part of it. How we'll name them and how we write the formula for these are much easier. What do I mean? Well, first off, the name will actually tell you the formula. If we're looking at our examples here to the side, I have the formula N2O. How do I name it? Dinitrogen, because I have two nitrogen. Monoxide, I have one oxygen. Dinitrogen monoxide, my formula will be N2O. Now, how we work with this is you name the first element as you normally would, using the full name of the element. So in this case, that's why it's dinitrogen instead of dinitride. Second, we're going to go ahead and name the the second element as if we would do the anion. So changing the ending to IDE. Now, if there's more than one of the element, we need to use prefixes, which are given to you on the next slide. Each prefix, most of them you'll be sort of familiar with, but you just want to pay attention to however many elements there are, or of that element there are, that's a prefix that you're going to use. So in this case, di, because I have two. Tri, because I have 3 oxygen here. Pent, because I have 5 chlorines. Those types of ideas. Now, mono is only used to indicate that there is more than one of the second element. So if you look back at our example here of carbon monoxide, you notice it's not monocarbon monoxide. It's just carbon monoxide. If there's more, as we have in these two examples, then we'll go ahead and use the prefix to show that there is more than one. This is where we were sort of looking at when we dealt with our law of multiple proportions. This is what it was sort of dealing with. All of these will always go back to a whole number ratio, but we can talk about that more later. Now, these are your prefixes. Many of them you'll be actually very familiar with. Mono, di, tri, tetra, and so forth. Make sure you have these memorized so you'll be able to utilize them as we go throughout the rest of the year. Now, last but not least, oops, lost my slide. Okay, last but not least, we have acids. And this is going to give you a little bit of a background on how to name them. We won't go over it in detail, but this is going to be very, very important as we get closer and closer to Unit 3. Because we're going to deal with acid-base interactions and reactions a little bit to give you a little bit of background on it. But we'll save that for another time. You may want to go ahead, pause it here, write down your, copy this chart into your notes so you'll be able to refer back to it when the time comes. I think this is where we're going to end it for now. I'll see you all tomorrow in class. Have a great afternoon and look forward to seeing you.